Hello everybody. Today I'm going to talk about another sampling-based path planning algorithm called the RRT star, which aims to offer a modification on the original RRT to tackle the problem of optimality. That's going to be presented by me, Ashraf Faraj, January 20, 2024. Now, as usual, this is the setting that we're going to use. As you can see here, that's the start node, that is the end node. The red circles are the obstacles. We're trying to find a collision-free path between the start and the goal nodes. Now, as we mentioned, we're going to discuss the RRT star algorithm. Now, the figure here shows a comparison between the different type of paths generated by a normal RRT, shown here on the left, and the RRT star, shown here to the right. Now, as you can see, there is a characteristic shape to the edges of the RRT star algorithm because they kind of tend to be more straight lines because they try to optimize the cost as much as possible. The cost being actually the path length in this case. And you can see here that the path that's actually found by the RRT star algorithm is shorter than the one found by the RRT. It can actually be proven that the RRT star algorithm, like the RRG algorithm discussed in an earlier video, is actually asymptotically optimal, meaning that as the number of the nodes tends to infinity, we are assured that we're going to find the optimal path. Now we're going to discuss the RRT star algorithm in detail. So first, we initialize the nodes to the start node and the edges to an empty list. We initialize the tree using the nodes and the edges. We now define a matrix called cost. The size of it is actually equal to the number of nodes. We initialize it at start to be equal to 0. Now this matrix will reflect, for example, for each node, for node maybe 3, for example, it will reflect the minimum length of the path that can be taken from the start node to that node 3. So this matrix right here stores the optimal length of the paths to each node in the tree. Now we are going to repeat the following steps for a maximum number of iterations n max. First, as usual, we're going to sample randomly from free space following a certain distribution list. Now we're going to follow a step that was actually similar to one found in the RRG algorithm. We're going to find a set of neighboring nodes to xrand within a radius r. Now these nodes will be parent candidates and we will store them in the xNeighbors variable. Now the next two steps are the two most important steps in the RRT star algorithm that actually differentiate it from classical random exploring trees algorithms. So now we're going to apply the function chooseParent. We're going to discuss it now in a few minutes. This function takes the set of neighboring nodes and xrand and chooses from this set of neighbors the parent to xrand with the minimal cost. So for example, we're going to add xrand to our tree. Now we scan the nodes in the neighbor set and we try to find the parent to xrand that will yield the minimal cost length to xrand if added to the tree. Now, the other important operation here is the rewire, which actually makes some changes to the tree and tries to change the edges locally in the xNeighbors set to decrease the cost of the neighbors as much as possible. Now, if the newest added node is in the goal region, then we just save the goal index and just continue this whole operation for a maximum number of iterations n max. Then we return the path to the goal if found. To discuss the chooseParent function, which takes the set of neighbors, and xrand, which is the point, the random point that we're trying to add to the tree. Now the figure here shows a simplified view of what is actually happening. So this right here is xrand, the random point that we're trying to add to the tree. This right here is the radius r in which we are going to find the neighbors. The neighbors right here are the following nodes. That's 1, 2, 3. Okay, so what we're actually going to try to do, first we're going to initialize the variable minimum to be the cost of the closest neighbor plus the cost of the transition from the closest neighbor to xrand. So this is just initialization for the min variable. Now, for every node that is found in X neighbors, we first try to extend from this parent to X rand. For example, we try to extend from here to here, from here to here, from here to here. So we might just sometimes find obstacles, we might not. So each different node will have a different extension. Now, if that extension is actually possible, and we found that the cost of connecting this parent to this random point is actually less than the minimum found so far, then we just substitute the minimum for this parent, and we just signal that the best parent that we just found is the current node X parent. Finally, after this whole scan is done, we choose best, the variable right here, as the parent to X rand, since it will yield the lowest cost to reach X rand from the start node. And you just update the tree to reflect the changes. That is, we add this edge from, for example, the best one, and we add X rand to the nodes list. Now, the second operation, probably the most important in the RRT star, is the rewiring. So this figure right here would show a simplified view of what's happening. So this again is the X new, which is the node that we just added. These are the neighbors. And right here, we have a node, let it be this. We'll call it X for our purposes. So what we're going to do is that we are going to scan through the X neighbors, which is all the nodes in this region. We're also going to test if we're able to extend from X new, which is the newly added node, to this X. Now, if that is possible, and we actually found that we can reach the node X right here through X new with a path that has a shorter length than the one we already stored, that is, if the cost of X new plus the cost of the transition from X new to X is less than the current cost to reach X, then we update the cost of X, we delete the previously formed edge between X and its parent, we add the new edge between X new and X, and we just here have to do another small step, which is that if X actually has different children, then when we update the cost of X, the cost of all of its children will also decrease. So this is what this function does. It just iterates through the children of X and updates their cost. And finally, we update the tree to reflect these changes, that is, the changes in the edges and the changes in the costs of the children. Now we present the results of the path planning using the RRT star algorithm. The figure here on the right shows the results of applying this algorithm to our test environment for the kilobot robot. Now we can see that the straight line edges, which are characteristic of the RRT star algorithm, are actually here exhibited clearly. We can also see that the RRT star algorithm is actually able to find the optimal path. As we can see here, straight lines from here to here, and then straight line from here to here. So the RRT star is actually asymptotically optimal, that is, given that the number of nodes tends to infinity, we are assured that we're going to find the optimal path. Now, as a conclusion, here in this project, we discussed the RRT star algorithm in detail. We implemented and tested the RRT star algorithm on the kilobot path planning problem. So just to recap a little bit, the RRT star was able to find the optimal path. It's also asymptotically optimal. That is, it can always find the optimal path if the number of nodes is large enough. And as we saw, this is actually a huge improvement on the RRG because it does not require that much memory, because it does not need to store that much edges. The graph is not complex, it's actually a tree, and it just utilizes the rewiring process to optimize the cost of each node. Now, actually, one of the problems of the RRT star algorithm is that it is actually kind of slow in conversions. This actually prompted researchers to find other variants of the RRT star algorithm that actually kind of increase the speed of conversions. We're going to discuss some of them in later videos. And that's it. Thank you for listening.